All right, hello, welcome back to lecture 9. And in this lecture, we're covering probably one of the strongest concepts in supervised machine learning that in my opinion, will rival neural networks for a while. And that's the notion of ensemble. So before we learn about like what these things are, I'd like to show you a video. And as you're watching this video, remind yourself that like we know machine learning models such as like the perceptron, logistic regression, right? Decision trees for classification. But we also know for like regression, we have like neural networks, we can do regression. We can do the linear regression with the single neuron. We can do regression trees, right? So we have like, we know these models, right? And each model, it learns on some data and then it can make predictions. So think of each one of these models as like a learner, right? Like, almost like a person, right? Before you watch this video.
We all need help, just different kinds. Maybe you need a little, maybe.
In there. Now there are.
Okay.
As a crowd, the patterns we make are incredibly predictable. Even as individuals, our actions are controlled by the code. And by untangling chaotic systems like the weather, we've uncovered evidence of the code in what we once thought of as impossibly complex. When we look at things from a different angle, surprising patterns emerge. Patterns that can reveal defining truths about ourselves and our future. In 1906, an unfortunate cow laid down its life for a place in mathematical history. 264, 417. The cow was the subject of a guess the weight competition at a village fair. The lucky person who came closest would win the slaughtered animal's meat.
2020. 2,130.
The amazing thing was, nobody guessed correctly.
170.
And yet, everybody got it right.
4,510.
To show you how they did it, I'm not going to use a cow. I'm going to use a jar of jelly beans.
450. 800. 12,000.
7,000.
How many jelly beans do you think there are in this jar?
80,000.
80,000.
No, actually, 50,000.
50,000?
Yeah.
Okay, there we go.
It's incredibly difficult for anyone to guess how many jelly beans there are. I asked 160 people, and most were way off the mark. Everything from 400 right up to 50,000 beans. In fact, only 4 people got anywhere near the correct answer of 4,510.
Plus 1,500. Plus 3,273. Plus 873. Plus.
But if I add all the answers together and take the average, I'll get the combined guess of the entire group.
500, 463, plus 853,000, plus 5,000, which gives a grand total of 722,383.5. Somebody thought there was half a bean in there. Now, there are 160 guesses made, so let's see how close they are collectively. Wow, that's extraordinary. If you remember, there were 4,510. The average guess to the nearest bean is 4,515. I mean, I thought it'd be close, but I didn't think it'd be that close. That is ridiculous. So although we had guesses that were all over the place, up in 30,000s, right down in the 400s, collectively, we get something which is just 0.1% away from the real number of beans in there. So as individuals, the guesses are just that, guesses. But when you take them collectively, they become something else entirely.
9,000.
What tends to happen is that, more or less, as many people will underestimate the number of jelly beans as overestimate it.
1,766.
A few people will be way off the mark either way, but that doesn't matter. Provided you ask enough people, the errors should cancel each other out.
700. The accuracy of the group is far greater than the individual. We call this the wisdom of the crowd.
Okay, so when watching that video, I've known about that video for a long time. I like it for some reason, but like in the context of machine learning though, right? Like imagine you have some models, right? Like whatever learners you want to pick from, like let's just say like a decision tree, right? Not even like, let's not even give it a name, just a learner. Let's call it a learner, right? Like each of the people guessing was almost like a learner, right? Like each person had like happened to have like different experiences like growing up in their lives, which is like their labeled data, right? And then when they encountered this jar, they were making a prediction on something they'd never seen before. So it's like the unseen data, right? But like each person individually was trained on their own experiences, their own set of data, right? And there's obviously like overlap between them, right? But because the observations that each person has made, there's slight variation in it, right? Then the variance between like the observation and their prediction is kind of canceled out. Like variance being like what they would do on like something they know how many beans are in, right? Versus this new jar they've never seen. Like the variance between the known things and the unknown jar that they saw, the variance between that. Like overall, if you average out all of their predictions, that variance goes away because of the different experiences that each learner has had. So that is the idea behind ensemble methods. Ensemble methods aggregate the predictions, and aggregation can be either regression, and like in the jelly bean, that'd be like regression, right? Or classification, you can aggregate and like take majority votes or other things like that. But ensemble methods are machine learning methods that aggregate the predictions of a group of base learners in order to form a single model. So like the 150 people that were surveyed would be like a single model prediction. They each made their own, but the aggregate was the actual prediction that was desired. So that concept is a very powerful concept in machine learning. And it still like surprises me how well it can perform, especially when the base learners are relatively dumb. And by that, I mean, you can take a collection of base learners whose like accuracy is just a little bit better than guessing. But if you have enough of them and you train them in the right way, given a data set, then collectively they can perform just as good as like a neural network or something. And there are two methods that we'll discuss, and these are bagging and random forests. Now, there is like one other method in the textbook that I encourage you to look at called group vote, where you have like, say you have like classification, you have a perceptron model, a logistic regression model, a classification tree, and like a neural network. These are all distinct models, train them on the same subset of data. And because they're different from each other, they're going to observe different variations in the features, right? That's one way. And again, I encourage you to like look at the book and do that. However, we're going to focus in on using one type of learner at a time, like kind of similar to like the video we just watched. They were all just people making guesses, right? So And we're going to start with bagging. Okay, so bagging is a term used in business. It's kind of confusing, but also in statistics and machine learning. And in statistics and machine learning, bagging refers to bootstrap aggregation or aggregating. Okay, and bootstrapping is a method of inferring results bootstrapping is a method of inferring results for a population from results found on a collection of smaller random samples of that population using replacement. It's important that there's replacement when doing this in order for it to be bootstrapping. It's called something else if you don't do that. So if you have some data that you're learning on and you have 3 different models, the same type of learner, like for example, a decision tree, then you can train each of those models on random subsets of the data. And they're going to observe different variations in the data, right? In the context of machine learning, a given set of machine learning models is trained respectively on random subsets of the training data with replacement, as shown here. And then the combined predictions of each model is aggregated and uses a single prediction. So average for regression or majority vote for classification. Okay, so generally speaking, with these types of ensemble methods, we're going to use dumb learners, as I was mentioning, meaning models that are barely superior to randomly guessing. Okay, and as I mentioned a second ago, individually the models will perform poorly, but collectively we'll see that they can perform well. So, but why is bagging useful? Well, I like this article here. I encourage you to go read it, but it basically comes down to eliminating variance between a model's in-sample and out-of-sample predictions, because that's the important thing, right? We want, if it's performing well in model, we want it to also be performing in a similar fashion on out-of-sample data. And one way of doing this is by aggregating the predictions of the base learners, because with this bagging method, they're each learning on like kind of random subsets of the data. So they're observing different things and they're making different predictions on those random subsets. So long as they're not overlapping every single time, because it is done randomly, then the variance between like their average predictions and what they predict out, it'll get smaller. So to illustrate this concept, we're going to consider the iris data set again. And we've probably noticed throughout the semester, there are 2 features and 2 species that have particularly difficult classification, as a classification problem. And that's the versicolor and virginica species and the sepal length and sepal width. So here, just import standard libraries, set my theme, load the iris data set, and then I'm grabbing the last 100 rows, which are the versicolor and virginica flowers, converting it to a NumPy array, make a little labels function here, apply that, and then convert it to a NumPy array for the labels. These are just like lists of strings for plotting purposes, and then I'm plotting. So as you can see, right, like this is not linearly separable in any sense of the word, and there's a lot of overlap here, right? So most of the models that we have would not be able to like do well on this binary classification problem, with the exception of possibly a decision tree. But decision trees also are prone to overfitting, okay, on training data and then performing poorly on out-of-sample data. So let's go ahead and make some training and testing data here. And here is a decision tree that we're going to try to compete against for classification accuracy on this data set. And then here, scikit-learn has a bagging classifier. And it's in the Ensemble module. So we're going to go ahead and say tree classifier is a decision tree classifier with the max depth of 15, set my random state to 42, fit it, predict, and then view the classification report. Okay. And then here, we're going to use a bagging classifier. Okay. Now, the first argument of this like class, when you instantiate it, is the learner that you want to use. Okay, so I've decided to use a decision tree classifier as my learner, but look at the max depth. It's 1. It's just 1 split. And this is called a decision stump. Okay, set the random state to 42. So what's interesting about doing that is that this is like depth 1 of this same exact tree here. Okay, I set the number of estimators equal to 100, but I can easily like change this to be 500 of them. It doesn't matter. Bootstrap is true. That's Ensample with replacement. So when it's exactly like this, like there's overlap possible. That's okay. And then in jobs here, this is a little bit computationally expensive. So in jobs equal to -1 sets it to use as many CPU cores for parallelizing this code. Okay. Then I fit it, predict, and look at his classification report. So let's see what this does. All right. So the accuracy for the decision tree on that data was 70% accurate, which that's probably the best we could have possibly done up until today. Out of all of the classification algorithms we know, that's the best we could have done on like, look at it, right? But then look at the accuracy for the random, like the bagged learner with decision stumps. Even though they were individually like awful, right? Like they would be terrible, right? In fact, like maybe we can even like look at that real fast. So let me just make another classifier here. So stump classifier equals to, just copy this, put it there, put the max depth at 1. I can just like copy all this business here. I just have to change this to stump classifier. Interesting. What just happened? Oh, somehow I think there was like maybe something didn't finish running, but that's interesting that the stump performed at 75% accurate there. The tree performed at 70. Like, so that's like weird, right? However, the bagged classifier, I must have like misread earlier, the accuracy is 78%. Yeah. So again, we've like increased the accuracy to probably the highest we've seen. And we can play with like the hyperparameters here. So like if I put like 500, does that make a difference? Yeah, so like 78 is getting up there, especially for that type of data. And this is being trained on like the training data, right? Like that's interesting to me. And then, but maybe we could get away with like doing like this if we decrease the max depth there. Still, like I don't think that any of the decision trees will like with that random state will get better than 75% accurate, but the bagged classifier is 78% accurate. So it's like pushing it, right? And then like if we want, we can look at the decision regions here. So look at this decision tree, decision region plot. This is like concerning to me. This is like, does anyone see why this would be concerning to me? Like surely like every single point that would appear there should be blue, right? Like maybe like not every point, but like the majority of them should be blue, but that's like a huge region right there. And then there's like this little like And it's like a pretty large region if you think about it in relation to the scale that we're looking at. So I think that this image here is very like it indicates that like how easy it is for trees to overfit. Okay, and then if we look at the bagged classifier, it's like a little bit more regular here. Yes, question. It has to do with the fact that, so the question was, so why did this one seem overfit and this one does not? It has to do with how each of those base learners were trained, right? They were trained and they were making kind of like wild kind of guesses in a sense all over the place, but there's like 500 of them. And if you average that out, those wild guesses and like that may be like really based off of their specific instances that they're in becomes like averaged out. Whereas this is just one tree that has been trained on all of the data, like not all of the data, all of the training data. So all of like the bias that it incurs in a sense is represented by that one tree and there's nothing to correct it. Whereas here, anytime there's some type of bias, there's probably like 300 other learners that are going to correct that overfitting tendency. But they also won't overfit on each one because they're only depth 1 trees. Okay. Now, this is an instance of a random forest. Okay, so a random forest is a collection of decision stumps. However, in scikit-learn, there is a distinction between using the bagging method here and actually implementing the decision tree classifier, however, the random forest, this should be the random forest classifier here. The algorithm used to train the random forest classifier in scikit-learn does not behave this way. There's an additional bit of randomness involved. So instead of making, so the decision stumps in the bagging method that we just did, it's making decision splits based off of impurity, like Gini index or entropy. In like, they're trying to like maximize the purity splits, right? That's also happening here, but it's done with random subsets of features. So instead of considering all the features, it takes random subsets of them and then finds the best split. So for example, there's only 2 features we're looking at right now. So when this is being trained, each decision stump is going to, instead of picking the best of x0 and x1, it's going to randomly pick one of them and then find the best split on that randomly chosen feature. So we're going to import random forest classifier. I suppose I did another split for some reason. Doesn't matter. So decision tree, so 15, next at 15, bagging classifier, and then random forest classifier. So here, max depth 1. So this is automatically making using decision trees. The number of estimators is 100. Bootstrap means with replacements. And in jobs is assigning it to CP cores. Right? And then fit and look at their classification reports. Question? It means that, so each learner, coming back up, so the question was, what do I mean by replacement? I mean that, like when this first decision stump is trained on this data, it's not removed from the data. So there's a chance that like this model might see a few of the points from there. Okay, so let's look at the classification reports. Bagging and forest did the same 75%, but I think what I did earlier was I increased it to like 500, but it should be the same. Still performing better than the single decision tree. But okay, so the accuracy is the same, but we should probably investigate like what's going on. Like what do the decision regions look like now? Do they look the same or not? So here again is the tree. Here is the bagged collection of decision stumps. There. It's almost like flat. There is a little line there. I think it's just the plotting didn't show it. But then let's look at the forest classifier. Different. Much different, right? In fact, I like this one, right? Just visual, like it's kind of like my visual bias on this, but you can see that there's a difference, right? And that's an important thing to note, and it's because the features are selected, like a random subset is selected to be used in the splits, whereas this is like trying to find like out of the two the best split always. This one it has to choose between, like sometimes it's forced to use X1 and it has to make, okay, this one. And then sometimes it's forced to use this one, right? So it introduces an extra bit of randomness. And I encourage you to read the textbook, and like this is a really important section. Read through it and you'll see a discussion about extremely randomized forests. It's almost like introducing more randomness. Well, it's not almost like introducing more randomness does lower the variance between in-sample and out-of-sample predictions. Okay. So maybe because this, like the random forest classifier is looking at random subsets, it might help to look at all the features and see what happens if we look at all the features and compare the performance. So here I look at the iris data set now with that there. Okay, so then all the features, same test size. I think my random state was 42 up there, so I'm going to put it back at 42. Let me make sure, because I want them to be very similar. Okay, so, all right, let's just see what happens. Interesting. It seemed like in this case, the tree did the best out of all of them. That's surprising. That's not what I was observing earlier. Oh, do I not have a random state here? That, let me make sure. Tree is that. Forgot that. Okay. I forgot to put 500 estimators. I doubt it's going to do any better than 95% accurate. Again, like what can we expect with that kind of data? But just because I'm curious, like I doubt it's going to do anything, I'll introduce like 1,000 estimators. That's like kind of unreasonable, but I'm curious to play with it real fast. And that just reduced it, right? So yes, question. Interesting. Are you playing? Are you changing? Well, the forest was doing better a second ago, but now they're the same. Once I changed it to, and now the forest is doing. I mean, the tree is doing better. Let's see. Random state 42. Random state 42. Random state 42. I wonder. It has to do, something is changing here. Something is changing here. Random state 2. Random state 42. Random state 42. Yeah. But that, like, I think it shouldn't matter if it's just that shouldn't change. So interesting. Well, let's look at their, like, well, we can't look at their decision regions, but still, maybe we can understand a little bit more about what's going on. And random forests help us with this, by the way. And they do that with this attribute, this class attribute called feature importance. So the names are sepal length, sepal width, petal length, petal width. For name, comma score, and zip names forest classifier dot feature importance. Let's print this out. So it seems that petal length and petal width are weighted as the most important for determining this accuracy. I'm still confused about why this is happening here, because that was not there when I was doing this earlier, and all the random states are the same. Yeah, but that's for the split. I don't know, like maybe. No, it says 42. Oh, yeah. Yeah. So I think that's maybe what it was earlier, is I didn't have the exact same random state. And again, you can play with that. So like here, it's better, right? So I guarantee you, like I haven't done this myself, but if you go through and you look through the possible like random states here, like on average, bagging is going to be slightly higher, or if like not the same as decision tree, and random forest is going to be like, it's like there's a hierarchy here on average. Okay. And again, the feature importance will probably be the same. Again, petal length and petal width are weighted the highest as important for classification. Okay, question. Well, it just depends on the problem. So the question was, if I'm saying that random forest is the best, but why would I do another method? Well, to be honest, a lot of problems, the best thing to do is a random forest. However, there are issues that can occur, right? So for example, I don't know if you noticed, but like I have 8 CPU cores in this computer, right? And it's parallelizing these all at the same time, and it still took a second, right? And this is a small problem, right? So as the number of data points increases, the number of your estimators needs to increase as well. So generally speaking, you like if you have like X data points, you will need X or more estimators. And if you have like thousands of data points, this can be computationally, it can be slow, right? Depending on like the application that you're looking at. And sometimes you don't even like need to do this, right? For like, if we had different features, we would just use like a perceptron or like a logistic regression to split it immediately, right? It just depends on the application that you're working with, what algorithm you're going to choose. But a lot of times, and like for a lot of problems, random forests are a good choice because they're descriptive. Though you can like measure feature importance, and the randomness involved will reduce the variance in the in-sample and out-of-sample predictions. Okay. But the general rule of thumb really is to use the simplest model possible, right? And it's kind of weird because random forests are relatively simple, right? It's a simple idea. So that's one of the reasons why people use them a lot. And they're good, as you can see, like 90% accuracy on like this data is like kind of that. I wouldn't think that, right? Like think about when we first learned about the perceptron and logistic regression, like it would perform horribly, right? So that's something that's very important. Also, on like bad notes that can happen with these things, just like decision trees are sensitive to rotation in data because of like how the decision boundaries are made with like orthogonal lines to the axes. If the data is rotated, which shouldn't change anything, it won't, right? It will change how the model will predict completely. Sometimes that's a consideration. Also, scaling of data, and that's something we haven't talked about yet that we need to very soon, which we'll probably do next week. Sometimes when the data is scaled a certain way, you might run into problems as well. But this is just a learning process. Like next week we'll encounter those kind of problems and then see like, okay, we'll have to figure out which model is going to be the best one to work. And, okay, so I think this is a good place to stop. It's about 1:50. Take a like 10-12 minute break and then come back and second part of the lecture. So I'm going to go ahead and stop the recording here.